Hi everyone, welcome back. Today we're going to be discussing logarithmic functions and their derivatives. I want to start off by discussing logarithmic functions. Now, using the algebraic definition for logarithmic functions, we can define a function to be a logarithmic function so long as we take the logarithm with a certain base of some number which we'll call x. In this particular case, b needs to keep the exact same requirements that we had when we were talking about the exponential base. If you remember in the previous section, we were looking at exponential functions, and we said with those exponential functions, our base had some restrictions. First restriction is that the base must be greater than 0. The other restriction is that the base cannot be 1. So once we apply this logarithmic definition, we can then start extracting how we're going to work with it a little bit more. Down below this logarithmic function, we see here that I have y is equal to logarithm base b of x. This works if and only if b to the power of y is equal to x, which means we have this sort of bridge between exponential and logarithmic functions. And if you remember from some algebra course, whether it was college algebra, intermediate algebra, or beginning algebra, that logarithmic functions and exponential functions are inverse functions of one another, meaning that they are operations that undo one another. Now, very similar, where we had properties of exponential functions, we will have properties of logarithms. And these properties of logarithms that we see on the left-hand side of the screen in orange are the logarithmic properties that we are going to be working with. Anytime that we have a logarithm with some base and we have multiples in the argument, then we can separate that logarithm into logarithm base b of x plus logarithm base b of y. In other words, that logarithm, that argument for the logarithm now gets split into the addition of the values that were in that logarithm. Logarithm base b of x divided by y. This now says that, very similar to multiplication that turned into addition under the logarithmic properties, division under logarithmic properties of an argument will turn into a subtraction of logarithms. So it's important for us to make sure that we make those distinctions and that we follow those properties, as they will become very beneficial in the future. Now, looking at the last property. The last property now says that if we take logarithm base b of some argument x to the power of r, then we can use the first property in the sense that an exponent is simply repeated multiplication, which means we're going to take the exponent r and multiply it by the logarithm base b of x. Great. Now, let's keep going. I also have a note on the right-hand side of the screen, and that note is in red. The reason it's in red is because it's going to be a very important note. That note says that logarithm base e of x is really the natural logarithm of x. Now, what does that mean? Well, that means that anytime that we have a natural log, it's simply telling us that we have a logarithm with a base of e. So we got to keep that in mind, and we're going to keep that in mind always. Now, for the next part, let's start introducing some calculus to this. If the base is greater than 1, then the logarithm, or in this particular case, the limit as x is approaching infinity for logarithm base b of x is going to be infinity. Now, what does this mean for us? Well, what that means for us is, if you see on the right hand side, I have a function here for a logarithm with a certain base that's greater than 1. So, if the logarithm base is greater than 1, as we keep proceeding through this, what's going to happen here is that as these x values get larger, these y values continue to grow without bound. In other words, there is no horizontal asymptote that this function will be capped off at. In other words, it's increasing without bound, therefore that limit will then be infinity. All right, not looking too bad. Next, as the limit of x is approaching 0, and notice, because we have a domain restriction on these x values, x can only be approaching 0 from one side, and that's the right-hand side. So as x is approaching 0 from the right-hand side, we then see that on this function, this logarithmic function, all of the outputs, or in this case the y values, they tend to grow faster and faster and faster down towards negative infinity. So we must make sure that we follow that process and that we follow these rules when we're talking about limits of these exponential functions. Now, before we go on any further in introducing more calculus to these logarithms, what I want to do at this point in time is I want to work with some examples that are going to help us outline the properties of exponents. So let's go through it. Here goes the examples. We want to express the quantity as a single logarithm. Alright, so we're going to have a first part to this, part A. This is going to be logarithm base 10 of 4 plus logarithm base 10 of a minus 1/3 logarithm base 10 of a plus 1. And then for part B, we are going to have 1/3 natural log of x plus 2 quantity cubed plus 1/2 multiplied by natural log of x minus natural log of x squared plus 3x plus 2 raised to the power of 2 and end that quantity. Perfect. So let's keep going with this. Working with part A. In part A, I want to make sure that all of these three terms are condensed into one singular term. And in order to do that, I need to make sure that all of the coefficients for each individual logarithm is 1 or -1. Because if it's -1, then that means that we're just going to be dividing by that argument. So within that process, I can say here that logarithm base 10 of 4 is going to stay the same. Logarithm base 10 of a is going to stay the same. However, working from left to right, these two logarithms have the same base, which means I will have logarithm base 10 of 4 times a. And then for this last logarithm, I have a minus 1/3. I'm going to keep the minus out in the front. However, the logarithm base 10 of a plus 1, I am going to raise to this power of 1/3. And that is using this third property in orange that we listed previously. I'm just using that property in reverse. And the reason I wanted to use that in reverse is because now every single coefficient for these logarithms is now either 1 or -1. In this particular case, because the logarithms are the exact same base, I can now divide by the argument for the logarithm that is being subtracted. So combining this, I get logarithm base 10 of the argument for a divided by the cube root of a plus 1. And that is one single logarithm. Now, some of you might be raising your hands if we were in class and asking, can we drop the number 10 from the logarithm as its base? My answer to that is yes, you can. You can write this answer as simply as logarithm of 4a divided by the cube root of a plus 1. There are certain variables or certain functions that take on certain exponents or coefficients that are kind of unspoken rules in math. Square root is one of them, where we have an index of 2, but we don't write it. Exponent of 1, we don't write whenever we have x to the power of 1, we just write x. Anytime that we write the number or the variable x, we have a coefficient of 1 multiplying it, but again, we don't write it. There are exceptions like that in math. Logarithm base 10 is another one of those exceptions. So working on the next example, part B. Again, if you want to work on this yourself, by all means, you can go ahead and put pause on the video and try it yourself. If not, we are going to work on it together. So let's go through. I'm trying to condense these terms into one singular logarithm. So what I'm going to do at this point in time is I am going to make sure all of the coefficients are either, let's say, manipulated by the properties, as in the first term, or I am going to distribute this 1/2 into those logarithms. So let's go through. Raising the first term to the power of 1/3, that means this 1/3 multiplied by the logarithm will turn into logarithm of x to the power of, logarithm of x plus 2 to the power of 3, and that's now going to be multiplied by 1/3 plus 1/2 times the natural log of x minus 1/2 times the natural log of x squared plus 3x plus 2 squared. Okay, everything's looking good so far. We're going to keep going. Let's start simplifying. Natural log of x plus 2. Pay attention to the exponent here. 3 times 1/3 is just 1. That means we're left as is. Plus, I want to remove that coefficient for the next term, that 1/2. So I am going to move this to the exponent of the argument. That means that we have natural log of x to the power of 1/2. And for the last one, I want to keep this negative out front. That's why I'm only going to move the 1/2 to that exponent. But notice that when I do it, 1/2 is going to multiply 2, which it will just get us natural log of x squared plus 3x plus 2. Look at that, real nice. Let's keep going. Now that we have all of the coefficients for the natural logs being either 1 or -1, what I'm going to do now is I'm going to use my properties of logarithms to condense all of this into one big logarithm. Which means I'm going to have the logarithm of x plus 2 multiplied by the square root of x. Square root of x comes from the second term. X to the power of 1/2 is square root of x, divided by this given trinomial, which is x squared plus 3x plus 2. So that's looking great now. If you can factor the argument, go ahead and do so. And that's what I want to do at this point in time, is I want to factor that denominator. Factoring that denominator now will get us, numerator stays the same, but factoring the denominator now gets us x plus 2 times x plus 1. And notice what happens here. Those factors of x plus 2 will simplify to just be a factor of 1, which means natural log here, natural log, we just end up with the square root of x divided by x plus 1. And that's all there is there, which is really, really good for us. That is awesome. All right, let's go ahead and let's talk about the change of base. All right, so the next part that I want to talk about is this change of base. And this change of base is going to become very, very beneficial for us, especially when we are going to try to take logarithmic derivatives in the next section. All right, so what I want to look at this particular point in time is this change of base, where it says that if we have a logarithm base b of x, then using the change of base, we can change this base to either a logarithm base 10 or a natural logarithm, whichever base we'd like. And the reason why we want to do that is because our calculators are naturally embedded with those features. Either a common logarithm, which is logarithm base 10, or a natural logarithm, which is a logarithm base e. If you see here on screen, I have 3 different versions of the logarithm. Down below, the very last option says logarithm base 6 of 5 is equal to that approximation of 0.89824444017. Notice all 3 options are the exact same number, whether we used a common logarithm, in other words logarithm of 5 divided by logarithm of 6, or whether we use a natural log, as in natural log of 5 divided by natural log of 6. All 3 options get us the exact same value, and that's exactly what we want to see. So as we proceed, we're going to keep this on the back of our mind, and we're going to be able to use that technique, using that change of base. So for this next example, I am going to solve each equation. And we're going to say solve for x. Part A is going to be the natural log of x squared minus 1 is equal to 3. Part B is going to be e to the power of 2x minus 3e to the x plus 2 is equal to 0. So let's go ahead and let's try to figure out what values we're going to need to solve these equations for x. Now, using the properties that we were looking at earlier, what I want to do then is I want to use the inverse operation here. So I'm going to raise both sides to the power of e, or if you want to think about it differently, then all we're doing is we are applying this logarithmic definition that we talked about at the very beginning. So where we were looking at only logarithm y is equal to logarithm base b of x if and only if b to the power of y is equal to x. That means that when I'm looking at this equation, the base here is e, so what I'm going to do is say that e to the power of 3 is then equal to x squared minus 1. And we could keep going with this process to say that x squared is going to be equal to e to the power of 3 plus 1. And then finally, we're going to get a result that says x is going to be equal to the square root. However, when you take a square root, it's always positive or negative. So positive or negative square root of e cubed plus 1. Now, you can verify by making the substitutions into the original equation, but you're going to see that those substitutions will always lead you to the correct answer, no matter which version we use for x. Which means these are both our, these both are our answers. Now, please make sure not to forget that positive or negative whenever you apply a square root. On to part B. For part B, what we're doing is we're looking to solve for x. However, in that process of trying to solve for x, we then start analyzing and start seeing that one term has e to the power of 2x and the other term just has e to the x. That to me stands out that this could possibly be a quadratic. So what I'm going to do is I'm going to factor that quadratic. Factoring this quadratic will then give me, will then give me e to the power of x and e to the power of x as my leading terms for my binomials. The last terms are going to be 2 and 1. Since the middle term is negative and the last term is positive, then both of these are going to be negative. That looks good. Now, by the zero product property factor, or by the zero product property, we get that e to the power of x minus 2 must be equal to 0, or e to the power of x minus 1 must be equal to 0. This tells us that e to the power of x must be equal to 2, or e to the power of x must be equal to 1. Now again, we have to try to solve for x. In order to solve for x, we need to eliminate this base. That way we can get x by itself. So applying that property or that definition of logarithms, I can then say if I have this exponential, then using this base in the logarithm for the argument of 2, we now get the natural log of 2, or same thing for this equation, we now get that x is equal to the natural log of 1. Now there's an issue with this, or small issue, that, or not necessarily an issue, but more of an observation. The observation is that this x value for natural log of 1 will get us 0. Natural log of 2 doesn't get us any nice number, it just stays as a natural log of 2. And again, you can go through and you can verify. Make these substitutions into your equation here and check to see if you get the same result. If when you take natural log of 2 and you insert into your original equation, you perform these operations, do you in fact get 0? When you insert 0 into these equations, do you in fact get 0 as your result? You will see that you do. And these are your two answers. So again, that's pretty awesome to see. Next, we're going to work on the last one, part C. Let's do a higher end problem here. So this higher end problem, natural log of 2x plus 1 is equal to 2 minus the natural log of x. All right, here we go. So what we want to do again is to make sure that we solve for the variable x. And in order to solve for the variable x in this particular case, what we have to do is we have to some way, somehow try to eliminate the logarithm, because that's where the issue stands. So I am going to get all of my terms onto one side of this equation as such. When I do this, I can now start looking at the left-hand side of this equation, because on the left-hand side of the equation, I can now see that I can combine these two logarithms. So let's go through and let's combine those logarithms. We now get natural log of x times 2x plus 1, which is equal to 2. Looking good so far. Let's distribute on the inside of that logarithm. So that's logarithm of 2x squared plus x is equal to 2. And we are going to continue to solve. So let's go ahead and let's eliminate this logarithm by using that definition for logarithms. What we're going to do is we're going to interpret this logarithm as an exponential, which means that we're going to have 2x squared, whoops, let's write that differently, 2x squared plus x is equal to e to the power of 2. Looking pretty good. Now I have to try to solve this. However, I'm working with a quadratic to solve for x, which that then tells us that we need to use some form of a quadratic formula or completing the square to try to figure out what this is going to be. So let's go through. This is now going to be 2x squared plus x minus e to the power of 2. Now, e to the power of 2, that's a constant. So what I want to do here is I want to use a quadratic formula. If you don't know the quadratic formula, my suggestion is get used to it. This quadratic formula is here to stay, and we will be using it a lot throughout this course, the next courses that you take, so on and so forth. It's always here to stay. So using the quadratic formula, what I'm going to do is I'm going to identify my a coefficient, my b, and my c coefficient. So in identifying this, I get that a is 2, b is 1, and then my c coefficient is negative e to the power of 2. So solving this, I now get x is equal to, well, let's go through, negative b, whoops, I put a double negative in there, sorry about that, negative b plus or minus square root of b squared minus 4 times a times c, all divided by 2a. Not too bad. Let's simplify. I'm going to bring the work up here. So let's keep simplifying. X is equal to negative 1, positive or negative, square root of 1, and then 4 times 2, that's going to be 8, negative and negative, that's going to be a positive, so it's going to be 1 plus 8 e to the power of 2. It's looking good because the radicand is positive, all divided by 4. Nice. Now, we have two different answers here. One of the answers is x is equal to negative 1 plus square root of 1 plus 8 e to the power of 2, all divided by 4. The other answer is x is equal to -1 minus square root of 1 plus 8 e to the power of 2, all divided by 4. So which answers are correct? Well, we're going to get started on that. The second answer that we get, -1 minus the square root of 1 plus 8e to the power of 2 all divided by 4, this numerator will always be negative. Negative numerator divided by a positive denominator will get us a negative value at all times. There's an issue with that. The domain of a natural log of x must always be positive. It must always be greater than 0. So for us, this answer, the second answer that we wrote down, is not going to suffice because it's going to get us a negative value. And I want you to take a look at the very first equation that was given on the right hand side. We have a natural log of x. So if we take this answer and if we insert it into natural log of x, we get an undefined value. Now for the next answer, -1 plus square root of 1 plus 8e squared. 1 plus 8e squared, this is the radicand. This radicand, because we have a 1 plus some other value, is always going to get us a number greater than 1. Which means we're in the clear to always get some positive number in that numerator and then divide that by 4. Which means, hey, we're all good. Our only answer here will then suffice to say that it will be -1 plus square root of 1 plus 8 times e to the power of 2, all divided by 4. Awesome. So that's a little bit more calculus style of logarithms that we want to find. Now let's work with finding an inverse function, which will kind of rely on some of the methods that we use in the previous sections. Here's the next example that I wanted to work on. This says find the inverse function for g of x, which is equal to logarithm base 4 of x cubed plus 2. So again, going through the process that we saw in the first section of this class, we want to go through and we want to assign y as the variable that we're using here for g of x, and then we keep log base 4 of x cubed plus 2 intact. Then we're going to go ahead and swap or interchange every x with y. So x is equal to log base 4 of y cubed plus 2. And finally, we are going to solve for y. So solving for y, that means that we need to eliminate the logarithm some way, somehow. And that is going to be by using the exponential function. So we should now be looking at 4 to the power of x is equal to y cubed plus 2. Now, if we're going to keep going here, we need to keep solving for y. Subtract 2. So we get 4x minus 2 is equal to y cubed. And then finally, we need to take the cube root of both sides, which means that we get the cube root of 4 to the power of x minus 2 is equal to y. And this now is the inverse function for g of x, which is the cube root of 4 to the power of x minus 2. Look at that. Awesome. That is great. So now that we have this momentum going for finding these inverse functions and for for solving all of these examples, what I want to do is I want to go ahead and establish limits. As we saw a little while ago, where we were in the lesson talking about these limits for these logarithms, and I'm scrolling on the page here, we see that we can apply limits to these logarithmic functions. So let's start looking at limits being applied to certain logarithmic functions. So on this example, we want to work with find the limit. and we're going to have part A, which is the limit as x is approaching 2 from the left-hand side for logarithm base 5 of 8x minus x to the 4th. Part B is going to be the limit as x is approaching 0 from the right-hand side for the natural log of sine of x. And the last one, part C, is going to be the limit as x is approaching infinity for the logarithm with an argument of 2 plus x, then minus another logarithm of 1 plus x. So we got these three examples that we are going to work with. So let's see what's going to happen here. Alright, so here we go. Part A. Looking at part A, what I'm looking at here is that the limit as x is approaching 2 from the left-hand side. So we got to keep that in mind. X is approaching 2 from the left-hand side. Because if you notice that if you make your substitution of 2 into your argument, then that means your argument will then turn into 0. And that's going to be an issue because logarithm base 5 of 0 does not exist. So that's where we then have to be very, very careful to try to think about how this is going to play out. Is this going to give us an asymptote that is going to lead us into an infinite positive direction, or is it going to lead us into a positive infinite direction? So did I say that right? Positive and negative direction? Something like that. There we go. All right, awesome. So when we start looking at this, now we have to try to figure out what direction is it going to take on. So let's go ahead and start looking at this. Logarithm base 5, I'm going to approach 2 from the left-hand side. That means that I'm going to be taking on the values from the left-hand side, meaning the values of either 0, 1, 1.5, 1.6, 1.7, 1.8, so on and so forth. That means that at this particular time, as I'm approaching 2 from the left-hand side, then these values here are going to get very, very small because they are approaching 0. Now, as these are getting very, very small, because they're both approaching the exact same value, they're going to keep getting smaller and smaller and smaller, meaning we're going to be approaching 0, 0, 0, closer and closer and closer for this logarithm base 5. This means that looking at logarithm base 5, as it's approaching 0, well, it can only be approaching 0 from one side, and that one side here is going to be making all of these values positive. So what does that mean for us? That means that this is going to be negative infinity. That's awesome. So again, we see this here just by using our process or our rules for these logarithms. The next one's going to be limit as x is approaching 0 from the right-hand side for sine of x. Now, if you remember sine of x at 0 is going to get us 0. But we're approaching this from the right-hand side. So what I want to look at when I'm talking about the right-hand side, what I'm looking at for the right-hand side when I'm talking about this logarithm here is 0. As I'm approaching x from the right-hand side, sine of 0 from the right-hand side will get us positive values. And these are going to be positive values that are going to be converging towards 0. So I want you to then think about natural log. Natural log for these values that are approaching 0. Well, natural log, as it's approaching 0, should get us negative infinity because, again, we're approaching that asymptote. For the final one, looking at the limit, whoa, okay, pause it there. I am sorry, this computer is going all wonky right now. That is weird. Technical difficulties here, everyone. Wow, so I have no idea what happened there. There we go, but it seems to be back on track now. So here, what I want to do is I want to try to condense this limit first, or this function first, to say that because two natural logarithms are being subtracted, then we must be able to combine them as 2 plus x divided by 1 plus x. And identifying this piece here, x is going towards infinity, but from Calc 1, we can kind of reimagine this argument by multiplying both numerator and denominator for this argument by 1 over x as such. In doing so, we now get the limit as x goes towards infinity for the natural log of, oops, let me go back, here we go, of 2 divided by x plus 1 divided by 1 over x plus 1. Now, as we see this here, the very first term, 2 divided by x, will now go to 0. The second term, 1 over x, will now go to 0 as x gets very large, which means we're really only left with the natural log of 1 divided by 1, which is 1, and naturally this becomes 0. Awesome. So as we start looking at this, we can now see applying these properties and applying these limits now starts to become a little bit more concrete and a little bit more easier for us to deal with these limits involving logarithms. So that concludes this lesson. I hope you all enjoyed it, and I will see you all for the next one, where we will be talking about the derivatives of these logarithmic functions.